Hello, amazing students. Today we're going to continue chapter 18 and we are going to talk about reaction quotient and also the equilibrium constant. So we've been talking about chemical reactions. Most of them are reversible, and that at some point reach equilibrium. And equilibrium happens when the rate of the forward reaction is equal to the rate of the reverse reaction. Now, chemists like to express things in numbers. They like things to be like black and white, like numbers, quantify things. And so they decided they were going to quantify the position of the reaction, whether it's at equilibrium or if it's still proceeding to the right or to the left to reach equilibrium, using amounts and using quantities. And so the chemists, a long time ago, came up with something called the reaction quotient. And the reaction quotient basically relates the amounts of the reactants and products to each other at a given set of conditions. So the reaction quotient, which is capital Q, because remember lowercase q is heat, so don't confuse the two. The reaction quotient is the ratio of product concentration to the reactant concentration, with each concentration raised to the power of the balancing coefficient. Now, it's a little confusing in words. It makes more sense when you see it as an equation. So let's take a look at this reaction here, same reaction that we saw on the previous slide. We have A reacting with B to yield C and D. Now, capital letters represent our formulas, our substances, whereas lowercase letters represent our coefficients. So if we want the reaction quotient, we want to calculate it or express it as an expression, we would take the concentration of each of the products. So here we have two products, C and D. So we write brackets, which means the molar concentration, and then we raise it to the power of its coefficient. So the concentration of C raised to its coefficient times the concentration of D raised to its coefficient, so the products, over the reactants. You do the same thing with the reactants. So concentration of A raised to its coefficient times the concentration of B raised to its coefficient. And again, the brackets mean molar concentrations, moles per liter. So let's take a look at some examples of things that I could ask you. So I could ask you to write the reaction quotient expression. Expression means like a formula or an equation as opposed to like an actual number. So if I give you this reaction, and this should be a reversible reaction. We have N2 reacting with 3H2 to produce 2NH3. We want the reaction quotient expression. So reaction quotient is Q, capital Q. It is equal to the concentration of the products. So we only have one product here, which is the ammonia. So the concentration of the ammonia raised to its coefficient, so raised to the second power, divided by the concentration of the reactant. So my first reactant is N2. Its coefficient is just 1, so you don't have to put it in there, times the concentration of my second reactant, which is H2, raised to its coefficient, so to the third power. So that would be my reaction quotient expression that I'm looking for. Let's take a look at the next example. So the next example says, what is the value? So they want an actual quantity or actual number, the value of the reaction quotient, if the concentrations for nitrogen, hydrogen, and ammonia are given to us respectively. So if this was the question, you'd write the reaction quotient expression first. So you'd write this out first, and then you just plug in your values. So my Q, we said, is equal to the concentration of the ammonia. And so the ammonia is 0.79 molar. And this is to the second power, divided by the concentration of the nitrogen, which is 0.55 molar. That's just raised to the first power, times the concentration of the hydrogen, which is 0.13 molar. and this is raised to the third power. So you punch this into your calculator, you get 516.5, which rounds to 520 with sig figs. Now for the units, each Q is going to have different units depending on what the coefficients are. So for example, this is molarity squared over molarity to the fourth, which ends up being 1 over molarity squared, right? Kind of confusing. Good news is you do not have to worry about units for this. So whenever you're calculating Q, you just look at the numerical value and you just leave it as is. So that's your answer. Now, as the reaction progresses, your Q is going to change, right? So we've been drawing these every time here. If you look at your concentration versus time, remember we said reactants start out pretty high, they decrease, and then over time they remain constant. Products increase, and then over time they remain constant. And again, your products might be higher or lower than your reactants, depending on what type of reaction you're doing, right? But the idea is that at equilibrium, so right here, you've reached equilibrium, your ratio of products to reactants should be the same, so that because your products and your reactants are not changing. So let's look at this a little bit closer. Q, we said, was the concentration of the products raised to the power of its coefficients divided by the reactants raised to the power of their coefficients, right? So at the very beginning of a reaction, if you look at this, time equals 0, you have no products, right? You don't start with any products. Products are at 0, right there. Reactants are pretty high, right? So 0 are your products over a big number. 0 over any number is 0, right? So your reaction quotient starts at 0, right? As time goes by, my products increase, my reactants decrease, and so I start getting a positive value, right? But then look at what happens when you reach equilibrium. Your products always remain the same. Your reactants always remain the same. So the ratio of products to reactants is going to become a constant. It's not going to change. Once you've reached equilibrium, as long as you remain at equilibrium, that ratio of products to reactants becomes a constant. So when you've reached equilibrium, because this ratio becomes a constant, instead of just calling it Q for reaction quotient, quotient, by the way, means like when you divide something, what's the answer? So instead of it just being a quotient, it becomes a constant at equilibrium. And so it gets a special name. We call it the equilibrium constant. And instead of calling it Q, we call it KEQ. In chemistry, we use K to represent a constant, and EQ stands for equilibrium. So this is the equilibrium constant. So the equilibrium constant K, or KEQ, is a special Q. It is Q when you're at equilibrium. So the equilibrium constant is the reaction quotient at equilibrium. So if I ask you, instead of to give me the expression for Q, what if I tell you give me the expression for KQ? Well, it's the same thing. The only difference is you plug in the concentrations at equilibrium as opposed to any other time in the reaction. So this slide is saying the same thing. So if you have a reaction A plus B yields C plus D, your equilibrium expression, your KQ expression, is the products over the reactants raised to the power of coefficients. So it's exactly the same expression as Q. Again, the only difference is these concentrations can't be at just any time. It has to be at equilibrium. That's the only difference. So some things to remember. If you are calculating KEQ, the equilibrium constant, remember that you have to use the concentrations at equilibrium. Another thing to remember, whether you're doing Q or KEQ, is that if you have heterogeneous reactions, meaning that you have reactants and products that are at different phases, you do not include any liquids or solids. You only include gases and aqueous phases. So if you have a reaction where you have solids and liquids, you ignore them when you write the Q or the KQ expression. We'll do a couple of examples where I'll show you what that means. The reason why you do not include the concentration of a pure liquid or a pure solid is because they don't have a concentration. Like if I tell you calculate the concentration of water, it's a pure liquid, you can't. There is no such thing. Concentration means solute in a solution, which means you're mixing two things together. So if you only have a pure solid or a pure liquid, you cannot have a concentration. The other thing to remember is it's always products over reactants, not the other way around. I always get one or two people that do reactants over products, so just watch out. So let's try some of these. We want to write the equilibrium expression for the following reactions. Now, whether I tell you write the equilibrium expression or if I tell you write the reaction quotient expression, you do it the same exact way. So you're going to write K as opposed to Q. You can write as K or K with subscript EQ, same thing, is equal to the concentration of the products or the concentration of the reactants raised to the power of their coefficients. So let's start with our products. My product is H2O, and it's raised to the second power divided by concentration of H2 raised to the second power times the concentration of O2 just raised to the first power. So exactly the same way we did Q. All right, next one. I'm going to write the KQ expression. You can write as K or KQ, same thing. So my first product is NO raised to the first power times the concentration of the H2 raised to the second power over the concentration of N2 just raised to the first power. And that's it. Why don't I include the water there? Well, because it tells me it's a liquid, as opposed to this water was a gas. We only include gases and aqueous solutions. We do not include any liquids or solids. All right, let's try the next one. K, or KQ, is equal to concentration of my HCl raised to the first power, and that's it. No solid, no solid, no liquid. I only include gases and aqueous solutions. Next one. K, or KEQ, is equal to concentration of CH3OH. This is methanol, by the way, the one that we use for celebrate birthdays. We light on fire on the table. Raised to the first power divided by the concentration of CO, times the concentration of H2 squared. So we include gases and aqueous solutions. We do not include liquids or solids. Let's try another. Actually, before we try another one, let's take a look at what is the whole point of this Q and KEQ and all that stuff. So, we said that Q or K, either one, is equal to the concentration of the products over the concentration of the reactants raised to the power of the coefficients, right? So, how do we use this? What does it mean? Well, what we can do if I have a reaction running and I don't know whether it has reached equilibrium or not, I can take a sample and inject it into GC or HPLC or some kind of, use some kind of spectroscopy to figure out what my concentrations are right now and compare it to what they should be at equilibrium, and this will tell me where is my reaction. So, let's say I take a sample of my reaction mixture, calculate Q. So right now, where I am, I take the concentration of the products over the reactants raised to the power of the coefficients. And I calculate that, and it turns out my Q is equal to K. K is the equilibrium constant, right? The equilibrium constant is usually like tabulated in books and stuff like that. So if they turn out to be equal to each other, well, that tells me, hey, I'm already at equilibrium. My forward rate is equal to my reverse rate. What if they're not equal? So what if my Q is smaller than K? What does that mean? Well, if Q is smaller than K, Q is where I am right now. K is where the reaction eventually will get to when it reaches equilibrium. So if my Q is too small, that means my product to reactant ratio is too small right now compared to what it should be at equilibrium. That means that the reaction is going to proceed to the right so that it reaches equilibrium. It's going to keep proceeding to the right, make more reactants turn into products. So my forward rate will be higher than my reverse rate. My forward rate will be higher so that I produce more products so that my ratio increases until it reaches what it should be at equilibrium. So if my Q is smaller than K, that means the reaction proceeds to the right. What if my Q is too large? So Q again is where I am right now. K is where I am going to be when I reach equilibrium. So if Q is too large compared to what it should be, that means my product to reactant ratio is too large. So which way would the reaction proceed in order to make that ratio small so that it reaches K? Well, if it's too big, I need to shift to the left, proceed to the left, use up some of the products, make some reactants, so that this ratio gets smaller until it reaches what it should be at equilibrium. So if Q is greater than K, that means my reaction will proceed to the left, meaning that the reverse rate will be faster than the forward rate for a little bit until you reach equilibrium. So that's the value of Q and its significance. The reason why we calculate Q is to compare it to K to see, is the reaction proceeding to the right, is it proceeding to the left, or is it already at equilibrium? How about K, the value of K itself? What does that tell us? Well, remember, K is the ratio of products to reactants. So, if this number has to be positive, right? Oops. Because molarities can only be positive, right? So that ratio will always be positive. If that ratio, if this number, if K, is greater than 1, what does that tell us? That tells us that I have more products at equilibrium than I do reactants. So if you remember, again, we keep drawing this graph. There's your concentration versus time. This graph looks like this. These are my reactants. These are my products. At equilibrium, I have more products than I do reactants. And so when I do this ratio, this number is bigger than this number, and so my ratio is greater than 1. Excuse me. If KQ is less than 1, that means that it looks like this. Here's my concentration. This is time. That means that at equilibrium, my reactants are more than my products. So because of that, this ratio, this number will be smaller than this number, and so my KQ will be less than 1. So the KQ value helps us figure out how much reactants to products I have at equilibrium. If it is product favored like this, or if it's reactant favored like this. So let's look at some examples of questions that I could ask you other than writing the K expression or the Q expression or calculating Q, here's another example. So at 2130 Celsius, KQ is equal to 0.0025 for this given reaction. Now, why is it significant that they give us the temperature? We don't actually have to use this temperature in any of the calculations, but KQ, or K, changes when the temperature changes. It's only a constant at a given temperature. So whenever you look up the value for K, whenever they give it to you, they have to tell you what temperature this is for, because temperature actually affects the value of K. What does this value of K tell us? Well, this is smaller than 1, so it tells us at equilibrium we have more reactants than we do product. So this reaction is reactant favored. All right, so they give us K, then they tell us, given that the concentration of N2, O2, and NO are given to us, we want to find Q, and also we want to predict how the reaction will proceed. So let's think about what they're asking us to do. They want us to find Q. So if they want Q, we write our Q expression first. Q is the concentration of the products, so the concentration of NO squared, over the concentration of the reactants, so N2 raised to the first power, times the concentration of O2 raised to the first power. That's the expression. It actually asks us to find what the value is, so we need to plug in our values and solve. Excuse me. So the concentration of the NO is 0.030 molar. And since we don't need units for Q, you don't have to put them in your work either. This is squared. Over the concentration of the N2, which is 0.81, times the concentration of the O2, which is 0.75. When you plug this in your calculator, you get 0.0015 as your answer. So we found Q. The second part of the question asks, predict how the reaction will proceed. So what you do is you compare your Q with your K. And so Q we said was 0.0015. We just calculated that. K was given to us. It's 0.0025. Which one's bigger? K is bigger. So you can think about it in two ways. Actually, three different things you could do. You could memorize one of the last slides that we looked at, the one that looked like this. You can memorize this and just go with that. You could think through it, which is what I usually do. So I always say my Q is products over reactants. And so right now my Q is too small compared to what it should be, because I'm 0.0015 and it should be 0.0025 at equilibrium. So my Q is too small, so that means I need to proceed to the right to make more products so that my Q equals to K. So the answer is proceeds to the right. Another way to do it, one of my friends that teaches chemistry shared this little tip with me. She said if you put K before Q and you write the inequality is the direction. It's like an arrow to show you which way it's proceeding. So K is greater than Q. So see how this looks like an arrow going that way to the right? So that means it proceeds to the right. So three different ways. Memorize it, think through the ratio, or use your direction of your inequality here. So the answer is it proceeds right. What does that mean? That means that for some time, it's going to proceed to the right, which means the forward rate will be faster than the reverse rate until it reaches equilibrium. Let's look at another example. So at 1,227 Celsius, KQ is 0.15. Again, whenever they list a K, they have to give you what temperature it is. And this one again, 0.15, that tells us that it's reactant favored because K is smaller than 1. Anyway, they give us the K, they give us the concentrations of SO2, O2, and SO3, and they ask us to find Q and also to predict how the reaction will proceed. So first step is write your Q expression. So my Q expression is equal to the concentration of SO3 squared over the concentration of the SO2 also squared times the concentration of O2. Then, because they asked to find what Q is, we are going to plug in our numbers. So my SO3 is 0.056 molar, that's squared, over my SO2 is 0.344, that is squared, and my O2 is 0.172. All right, the answer is rounded to 2 sig figs is 0.15. So we compare, that's our answer to answer what is Q, and then to answer how it proceeds, you compare K with Q. Q we just calculated to be 0.15. K is given to us, it's 0.15. They are equal to each other. So what does that mean? That means you are already at equilibrium. Your forward rate is already equal to the reverse rate. Let's do one more of these. So same thing. We're given K at a certain temperature. It is smaller than 1, so again, reactant favored. And we're given the reaction, we're given the concentrations, and we're asked to find Q and how the reaction proceeds. So same as the last two examples. So we're going to write our Q expression first. Q is equal to the concentration of the H2O cubed over the concentration of the H2 cubed. Why did I leave out the Fe and the Fe2O3? Because they are solids. So they don't count. We only count gases and aqueous solutions. Now we plug in our values. Our H2O is 0.37 molar, and that's cubed, over our H2 is 0.45 molar, and that is cubed. Let's calculate that. The answer rounded to 2 sig figs is 0.56. And then we are going to compare our K with our Q in order to see which way it proceeds. So our Q we just calculated to be 0.56. Our K is 0.064. And so our K is larger, our K is smaller than our Q. 0.56 is much larger than 0.064, right? So K is smaller. And so either memorize it or think through it. It's products over reactants. And so my Q is too large, so then it's going to shift to the left to use up my products to make this number smaller, or to make more reactants to make this number bigger, so that my Q gets smaller to equal to my K. Or you can use the tip where you look at the inequality. This is going to the left, and so it proceeds left. That means that the reverse rate is faster than the forward rate for a little bit until it reaches equilibrium. That is it for K and KQ. Have a wonderful rest of your day.